Hello everyone, I'm Markus, and I want to talk to you about crossing numbers, just the normal standard crossing numbers, and I will focus on complexity and algorithmic aspects of it. I will not go deeply into any graph theory stuff. There is a lot to be said about graph theoretical questions in terms of crossing number. I will not touch upon them deeply because there just isn't enough time to do so. If you are really not familiar with the crossing number, I'm pretty sure that this will change either now or at the latest when you're at the conference on Thursday and Friday and Wednesday. There will be plenty of talks doing some things with the crossing number. The crossing number problem goes back to the time of the Second World War when Paul Turan was forced to work in a labor camp where they were making bricks, and he had to push carts of bricks from the kilns to the storage yards along some rail system, and whenever there was a crossing in the rail system, these tracks would just make the carts lose their track, and the bricks would fall off the carts, and it's just even more work and more hard work than it already was. So he was really thinking about how can I lay out the rail system connecting the kilns and the yards such that there are as few crossings of these rails as possible. And this is kind of the birthplace of the crossing number problem, which he states for the problem of complete bipartite graphs. And in this drawing here, you can see that we have 3 such crossings. We could improve upon that with having only a single crossing, but since this is, in graph theory, a K33, you will not be able to do it without any crossings. We will start with formally defining the crossing number, because that is surprisingly nasty to get right, and it's very, very easy to come up with something that sounds and feels like the crossing number, but is actually something related but different. Then we'll discuss how hard it is to solve the crossing number problem. And then we'll look into algorithmic aspects. We'll think about how can we solve it exactly, despite the fact that it's NP-hard. We'll discuss how to solve it heuristically, and we'll look at approximation algorithms for the crossing number problem. So how can we define the crossing number? First, we need to start with a drawing. So a good drawing is just a mapping of the vertices into points in the plane, and the edges are mapped to some curves connecting these endpoints. The curves may be straight lines, they may be some wiggly lines like here. I don't care. They connect the endpoints. And I have certain specific properties that make that a good drawing. In particular, no edge passes through another vertex point like you see here, because you wouldn't be able to see if this is one red edge or if it's actually 2 edges connecting to this middle point, right? So something like this is not allowed. Similarly, we do not allow 2 edge curves to have an infinite number of points in common. You only want to have finitely many points, because here, when you look about it, the red and the black edge, they are kind of running here along in parallel on top of each other, and you have no way of knowing which edge is which at the end of it if you don't have the colors. So only a finite number of common points. And we also want that no 3 edge curves have a common point in their interior. Like this crossing point of 3 edges, you don't want that, and you actually don't need it. If you have a drawing like this, you can just shift around a bit, move one edge a tiny little bit to the left or to the right, and then it would just be 3 crossing points. So a crossing then is really a non-vertex point in the plane that is common to 2 edge curves. As you see in the top picture, this is a drawing with 6 crossings, and the crossing number then is just the smallest number of crossings over all possible good drawings of the graph. Simple enough definition. the definition becomes a bit muddied once you think about it longer, because you very soon realize that you do not need to allow all different drawings in the graph. You can just consider simple drawings of simple graphs, so there are no multi-edges in the graph, and then we know that there is no good reason for an edge to cross itself, because if an edge would cross itself, we can just drop the loop in between and still have a reasonable drawing of the graph, and it has one crossing less. So the optimal crossing number will never be attained if you have self-crossings of the edges. Similarly, no pair of edges will have more than one common point. If you have two common interior points like so, you can just reroute the red edge along the blue edge. If along the blue edge you have at most as many crossings as on the red edge, and you get rid of these two crossing points. So you would improve the crossing number, so the optimal crossing number drawing will not have two crossings on edge pair. And similarly, there is another case that two edge curves may have 2 points in common. If they are adjacent, so they have a common vertex point, that's fine. And then if they have another point like here, which is a crossing, you again can just reroute the red edge to get rid of this one crossing. So you can assume that you always get the optimal crossing number with a simple drawing. The point is, this opens the room for you to think of other, slightly different definitions. Like when you think about a drawing where two edges have more than one crossing in common. Okay? So they have 17 crossings amongst each other. Then you can just think, well, okay, I have 17 crossings. Whenever I take two of them, I can run this post-processing to get rid of pairs of crossings. So I will get down from 17 crossings to 15, to 13, to 11, and so on, and end up with one crossing. And the same is true if I have a drawing with 8 crossings. I can just pairwise get rid of them, and the edges will not cross in the end. So I could just directly say, well, I'm just counting the number of edge pairs that cross an odd number of times, because in all the other cases, I can get rid of these crossings. This crossing number is known as the odd crossing number. You only count the number of edge pairs that cross an odd number of times. Interestingly, if you define it like this, there is an example of a graph which has a different crossing number than its odd crossing number. It's a very weird construction. And the point really is that just because you can do this post-processing does not go vice versa. You could benefit from the fact that you can avoid some other crossings by putting many crossings on the same edge pairs if you only count them a few times. There is a very nice paper by Pach and Todd with the funny title of Which Crossing Number Is It Anyway?, which goes into the details of how simple deviations from the normal definition give you potentially different crossing numbers. And some of these other definitions, it's still open whether they are the same as the normal crossing number or not. And if you want to read 100 pages, then you're invited to read Markus Schäfer's wonderful paper on different crossing number variants, where he collects a bunch of those. So back to the normal crossing number, we know for a very long time that it's an NP-hard problem. So that means given a graph and some integer number k, we want to know whether the graph G has a crossing number of at most k, and this problem is NP complete. So that means if your complexity theory class is some years ago, that just means that you will probably not be able to figure out the correct crossing number in polynomial time, but once I show you a drawing, you can check in polynomial time that this drawing really attains a crossing number of at most k. How does this proof work? The proof for NP completeness, I know it's probably old buried memories full of disgust for some of you, but it's actually very nice to do NP-completeness proofs. What you have to do in NP-completeness proofs is you start with a problem for which you know that it's a hard problem, and then you reduce it to your problem. And you say, well, this other problem that I know that is hard is actually kind of a special case of the problem I'm interested in. And because this special case is already hard, of course my problem will be hard as well. So this problem with which we start in Gary and Johnson's proofs is the optimal linear arrangement problem, or OLA for short. There you are given a graph, like the colorful graph here, and you want to find a permutation of the vertices along this line here, such that when you look at the distance of the vertices that are connected by an edge, and you count the length of each edge, the sum of all the edge length is minimized. That's the optimal linear arrangement. Arrange the vertices linearly such that the sum of the edge length is minimized. A well-known NP-complete problem. And we now want to show that finding the crossing number actually is at least as hard as this problem. To do that, we start with any problem instance of that type and transform it into a crossing number problem. Well, what Gary and Johnson did is they didn't go directly to the crossing number. They had some problem as an in-between, which is the bipartite crossing number. The bipartite crossing number says, well, I am given a bipartite graph. Some vertices, the first partition set is on the top layer, the second partition is on the second layer, and all the edges need to be drawn as straight lines between these layers. So it's really just a question of finding a permutation of the top and the bottom layer such that the number of crossings is minimized. And the graph that you construct from the graph that is an optimal linear arrangement problem just works like this. For any vertex you have in this graph here, you have two vertices in your bipartite graph. Like for the red vertex, you have two red vertices here in the bipartite graph, and you join these two vertices with many, many parallel edges. Which means that you really do not want to cross over what is here drawn as this thick gray thing here. And you do this for every vertex. And because this is very thick, it's clear that the optimal solution will not have green edges crossing amongst each other. So they will be well separated. So you will have one permutation of the vertices on top and the same permutation for the vertices on the bottom, because the gray lines will not cross. And now you have the original edges here, which you draw from bottom to top in this diagram. And, well, like the green edge goes from the red vertex to the orange vertex without any crossing. Very nice. The turquoise one, well, it has to cross over here. The light green one has to cross two of these gray bars, if you want. So the problem really is the permutation that you achieve here, which attains the smallest number of crossings, will just be one where you have as few crossings of colored edges with the gray edges. And the longer such a colored edge is, the more gray edges it crosses. So it's really the same problem. If you find the optimal crossing number for this permutation will also be an optimal permutation for the OLA. So since figuring out this problem is hard, this problem needs to be hard as well. But this is not the normal crossing number, because I have this fixed placement of the vertices on these layers. So what Gary and Johnson did is, well, they just they are now thinking about, okay, give me any bipartite graph with the bipartite crossing number problem. And now I want to show, since I know that the bipartite graph problem is already a hard problem, I just transform it further into a normal crossing number problem. And all I have to do is, I have the red graph here that is just the instance of a bipartite crossing number problem, hard problem. And now I attach, again, thick gray edges here, and each thick gray edge, again, is a number of many, many parallel edges. So you really do not want to cross them. And since this is kind of a tree, it only leaves one outer face where you have to place all the red vertices, and you can always perturb that drawing such that it then looks like a two-layer drawing. And by minimizing the crossing number in this large graph, you also solve the issue of minimizing the crossing number in the bipartite graph. So since the bipartite graph problem is hard, the general problem needs to be hard as well. That was the proof in the 80s, and by today's standard in graph theory and crossing number research, we would probably just not be very happy with that proof. Because on some very high level, this proof is utterly stupid. Because these are not the graphs that we really care about. These are stupid graphs because they have many, many parallel edges. Typically, we are interested in graph theory with simple graphs. So no parallel edges. And you cannot do these constructions without parallel edges. And at the same time, not only do I have parallel edges, I only have very, very high maximum degrees in these graphs. Like, if you think about this black vertex here, it has like n many gray edges. And each gray edge is an enormous amount of parallel edges, really. So you have a high maximum degree, and you don't want that. And it took quite some time until Chimani showed that actually the crossing number is hard even for interesting graphs, more reasonable graphs. So he showed the problem is hard even if I think about only simple graphs, and these graphs have a maximum degree of 3. Maximum degree of 3 are the first non-planar graphs. If you only have degree of max 2, then we're just talking about a bunch of circles and paths, so not much interesting going on there. How does this proof by Chimani work? Well, the idea is essentially the same, because we again start from the optimal linear arrangement, but we do not go to the bipartite crossing number case, but directly to the crossing number. What is the idea? We start with 2 concentric rings. Like you have this gray ring, and then you have this is either a ring or a filled circle, it doesn't really matter. And between those, you have these spokes. There are a couple of spokes. And just to make sure, all of the pictures I'm showing you are essentially lies. They are much simplified just to get across what the construction is about. It's not like the real construction there. You need to be very careful with the number of attachment points and everything. But the point is that you have these large rings, and these rings are really grids of cubic graphs, like this bricklaying structure that you have here. This is just a grid where every vertex has degree 3, and you can attach stuff on the outside of this ring by just placing an inner vertex here, which would have degree 2, and then you attach an additional edge to it, and it again only has degree 3. So you can build this structure. And now, for every vertex in your instance of the OLE instance, you just construct yet another ring. And each ring, again, is just a thick enough ring consisting of this substructure. And you have a ring for the red vertex, and a ring for the orange, for the green, for the violet, and for the turquoise. And now these are just rings. They're not yet attached to the whole construction. So I will have some kind of construction that attaches each ring to one of those spokes, or actually to multiple of those spokes. And the idea is, if you do it correctly, then you can still permute the rings. So you can just draw the red ring here on the outside, or you can just move it, I don't know, perhaps here in between the violet and the turquoise ring. So you are still free to permute all these rings, which is kind of the problem now. How do you permute these rings? Because that's the permutation along the linear line. And then all you need to do is for every edge in your optimal linear arrangement graph, you just attach essentially an edge connecting the 2 corresponding rings to each other. And depending on the permutation, you want to have this turquoise edge from the red ring to the green ring, and in the permutation as you have now, you will have to cross over this orange ring. And crossing over a ring, the ring has a certain thickness, then you just know how many rings are crossed overall, and these are all the crossings that you really care about. So it just boils down of finding good permutation of the rings in order to minimize the number of crossings of these colored edges. All other crossings are there anyhow in an optimal drawing. So this is the idea how Chimani showed that these graphs are simple graphs, they're cubic graphs, so maximum degree 3, and the crossing number is still hard. Okay. Well, we can go even further. We can think about even simpler graphs and argue that optimizing the crossing number or finding the optimal crossing number, even for simpler graphs, is a hard problem. And that's what Sergio Gabello and Boya Mohar did. They showed that, yeah, well, it's hard for simple cubic graphs, but it's even hard if these graphs are essentially planar and there's just one additional edge. If this one single edge E wouldn't be there, it would be a planar graph. No crossing number that I need, just crossing number 0. And there's just one additional edge coming to it. And suddenly, figuring out the optimal crossing number of this graph becomes a hard problem, just because of this one edge. This construction does not use the optimal linear arrangement, but a pretty nice other idea. The idea is that they come from the master of all NP-complete problems, the SAT problem, and it reduces to some special so-called anchored crossing number on disks. We'll get the gist of it in a second, and from that problem you go to the crossing number. What is this anchored business? The idea is you want to draw a graph only on a disk. So you're given a disk with a circular boundary, and you're only allowed to draw inside the disk, not outside. And some of the vertices are anchored at the border of the disk, and you know there's cyclic rotation on the disk. And you want to draw the graph. And now this is actually a much simpler instance that they construct is there are two graphs, essentially, which are each planar. You have a red graph and a blue graph, both of which are embedded in the disk planarly, even uniquely. And they can show that coming from any subformula, you can reduce the subformula to look like this instance. We're not going to discuss how to do that. The point now is if you are given this instance, what you want to draw is you want to draw both of them simultaneously within that disk such that the number of crossings between red and blue edges is minimized. And just intuitively speaking, this is a hard problem. We can just believe that for now. Okay, that should be good enough. We believe that this is a hard problem, but here you have many, many crossings. But this graph is far from being a planar graph plus one additional edge. Because this graph, as a graph, is actually a planar graph, if you think about it. Because if you would just draw it normally and not on a disk, there would be the whole outside for you to draw on. So you could just take the whole blue stuff and draw it outside and draw the whole red stuff inside. And you can draw it without any crossings. So now to go from this problem to the crossing number problem, we are not allowed to have these restrictions with anchors and inside of a disk stuff. But the idea is really simple again. Instead of having a disk, you connect these two vertices with a bunch of paths of length 2, but very many of them. So over this circlic dark gray boundary, you do not want to cross, because having an edge crossing over such a piece would incur an enormous amount of crossings, much larger than the optimal crossing number. So you're not going to do that. But then still you could draw the red graph inside and the blue graph outside. Well, but I'm now attaching a single additional edge from one vertex in the blue graph to one vertex in the red graph. And this violet edge here, if I would draw the blue on the inside, the red on the outside, this violet edge would have to go from the inside to the outside and cross the circular boundary. That is too expensive, so that is nothing that we will do in our solution. So we are stuck with drawing both red and blue within the circle. And just because of this one single edge, we now have to deal with the problem of optimizing for all of these crossings in there. And that's why this problem is, again, hard, just because one edge too much is in the graph. Crossing number is a tough problem also from the decomposition point of view. I guess we all know that many interesting graph problems become simpler when you have a bounded tree width, or at least when you have a bounded path width. Bounded path width graphs, they are really simple. No problem can be too hard on those, right? Well, crossing number is just recently it was shown that if I'm just looking at simple graphs and they have bounded path width or bounded tree width, I don't recall the correct numbers, but I think it's something like bounded path width of 12 and bounded tree width of 7 or 9 or something like that, and suddenly you already have a hard problem again. Also, there is a proof, not totally unlike to the proof we have seen up here for the nearly planar graphs, that the crossing number is APX hard. What does APX hard mean? Well, it's hard to approximate in the sense that you will not be able to find a p-TUS or even an f-p-TUS for it. So it may be that you can approximate it within a constant factor, like twice the number of crossings than the optimal, but APX hardness means you cannot go beyond that. There is not the possibility within polynomial time, unless p equals np, that you will be able to find an approximation within a ratio of 1 plus epsilon for an epsilon that you are free to choose. Which is, when you think about it, not a very strong assumption, because it's weird to be able to approximate something that well. And we're typically happy with some constant factor approximation. It turns out we don't know any constant factor approximation for the problem. But the lower bound we have is much lower. It just says, well, we cannot go arbitrarily close. Well, on to the good news. The problem is fixed parameter tractable. That means with its natural parameterization, the crossing number itself, we can test whether a graph has a crossing number at most k in a running time that is only polynomial in the input size if we allow the algorithm to be exponential or higher dependent on some parameter k, where k in our case is the crossing number itself. So we can test whether a graph has crossing number at most k in a running time f of k times n squared. That's what Grohe showed. As long as fk is computable, that means that you have a fixed parameter tractable problem. The issue is, of course, that this f to the k that he proved was something like 2 to the 2 to the 2 to the 2 to the k. Crossing number 1 seems to be within reach. Higher, probably not. This result was improved a couple of times. The current best result shows you something like 2 to the k log k only times a linear function in n, but it has an enormous amount of hidden constants in the big O notation, and this algorithm, as is the case with all of these algorithms since Grohe, none of them will work in practice. You shouldn't even try to implement them. It's just a horrible mess. You're not going to get anywhere with it. But at least we have the theoretical result that it would be possible. Similarly, we know that the crossing number is fixed parameter tractable if I parameterize it with the vertex cover number. So if I know I can cover my whole graph with only k many vertices, so I can pick k vertices and every edge of the graph is attached to one of those at least, and k is small, then I again can have an algorithm polynomial in the graph size times some function of k. Both the algorithm is not very practical because it's a huge enumeration it needs to do, and the vertex cover number is supposed to be large on interesting graphs. So it's also not very helpful. If you really want to solve the crossing number optimally, there are other ways, like integer linear programs, and I only want to give you the gist of it. The idea is that you start with a binary variable for every edge pair that may cross, and so the variable xef should be 1 if and only if the edge E crosses the edge F and 0 otherwise. Then I can just rephrase my optimality question to minimize the sum of all these binary variables. This will then be the minimum number of crossings. And now, since this is an integer linear program, I have to find some linear constraints which force me to actually set some of these variables to a value different to 0. The idea is very, very straightforward. We know that a graph is non-planar if it contains a so-called Kuratowski subdivision, a subdivision of a K5 or a K3-3. So I could just go over all of these subdivisions I have in my graph. Granted, it's an exponential number, but who cares? I go about all these, and for each Kuratowski subdivision, I write an equation that just says, well, consider all the crossings I could have between edges of this subdivision. Since this subdivision is not planar, there needs to be at least one crossing amongst these edges. And that's all that this constraint tells you. You look at the subdivision, there needs to be at least one crossing. The sum of these variables needs to be at least one. And that's the system that you want to solve. Ignoring the fact that you have an exponential number of Kuratowski constraints, it even doesn't help you to solve that problem. Because we know from the 90s, essentially, that the so-called realization problem already is NP-complete. So even if I give you a solution to this ILP, even if I tell you the edges that cross in the optimal drawing, I give you a complete set of edge pairs and say, these are the edges that cross. And I just ask you, did I lie to you, or is there really a feasible drawing where precisely these pairs cross? You will not be able to resolve that within polynomial time. Already that problem is hard. Why is it hard? It would be very simple if every edge is involved in at most one crossing. Because then, whenever two edges cross, you can just place a dummy vertex on that crossing, and then in the end you run a planarity test and see if you ended up with a good drawing. The problem really is that some edges may be involved in multiple crossings, like the black edge here may be crossed by the red edge and by the blue edge. But I have no idea whether the crossing with the red edge comes before the one with the blue edge or the other way around. And just figuring out whether there is some permutation of these crossings along the edges is an NP-complete problem. So this ILP, as I have sketched it up there, doesn't help you anything. You need to enrich the model to also take care of these issues. And there are only two ways that we know of how we can do that. One way is to subdivide all these edges. Like when we know we have some upper bound on the crossing number, well, in the worst case, every edge crosses every other edge, so it's just m squared. So I just subdivide every edge many, many times, and then I force every edge to be involved in at most one crossing. Then the realization problem goes away, because every edge is involved in only one crossing. But this comes at the cost that every edge now became a path of enormous length. The other idea is to add linear ordering polytopes, so the linear ordering problem for each edge, and enrich the problem with that, which is just mathematically much more messy, but it works out faster in practice. independent on which route you take. In both cases, you have too many constraints to easily solve it because you have to do something for every Kuratowski subdivision, and you have too many variables to do anything reasonable about it. So you need to generate both variables and constraints on the fly in order to solve it. So you need a branch and cut and price framework, which is very nasty. But it works in practice together with strong heuristics, as we will see later on, and some other algorithmic tricks. We are able to solve simple, sparse graphs that do not have a high crossing number. These are just rough values. I could just write any other number here as well. All of these numbers are lies, essentially, because there are graphs with these parameters which are easy to solve and others which are hard to solve. That's just kind of the rough estimate of what you can actually do with them. The real issue is that these algorithms are very tough to implement and even tougher to debug and to check for correctness. We can only hope that we implement them correctly. There may be some weird bugs. And even if we implement it correctly, there's an LP solver which only does floating point operations, and there may be numerical issues in the model. So can we really trust if this algorithm tells us what the exact crossing number of a graph is? Well, typically not, but there is a way to generate independent checkable proofs from it, and you can even do it online. And the idea is that you have the compute server somewhere which solves both of these ILP models, and it computes the crossing number. And once I know the crossing number, I can restart the computation now that I have the perfect upper bound, because I know the solution, and I just recompute it. And from this recomputation, I can then extract a proof, just an XML file that describes the situation why the crossing number has to be as such. And this proof you can then independently check on any other old computer with some. You don't need any ILP solver. You do need an LP solver, but for that there are exact LP solvers which do not do floating point operations, so they do work exactly, and those you then can use to verify those proofs. Okay, but this only gets you so far. Only very simple graphs are you're able to solve with that. What else is there to do? Well, one idea is to consider the so-called single edge insertion number. You're given a graph which constitutes of a planar graph H and one additional edge. Just like what we discussed before, finding the crossing number of this graph G, which is H plus E, is still an NP-complete problem. But the insertion problem is now slightly different because it asks for what is the best crossing number I can attain if I restrict myself to plain drawings of H. So I'm not allowed to have any crossings on the planar graph itself, with itself, and all the crossings are collected by this one additional edge. And if you have a drawing like this, there are many possible routes you could take to embed the red line here, and it's a very simple problem if you just consider H to be embedded. If you have a fixed embedding, a fixed rotation scheme for H, then this is just breadth first search in the dual graph. Very simple. It's harder if I ask you just to say, well, draw H planarly, but I don't care which embedding, just find the best embedding. Then in this case, you will probably realize that this piece here is only attached to the rest of the graph at 2 points. So I can flip it up and down. And if I flip it around in a clever way, then I can now add this red line with only one crossing, which was not possible before. Figuring out the best embedding is an algorithm known for 20 years by now. Linear time algorithm works very, very smoothly in practice. It's not so easy that I can just briefly describe it to you. Last year, for those of you who have been here, I know at least one who was here last year. Philip had a very nice talk last year describing just this one algorithm and a bit on the surrounding, but essentially concentrating on that algorithm. So we will not discuss that in detail. I really only want to give you the gist of it, kind of the key idea, and you are not supposed to understand all the details of it, just because for what I'm going to talk about later, we'll need that as kind of a black boxy thing. So the idea for the single edge insertion is that you really run it in two phases. First, you just ask for the best embedding of the graph H, into which you will then insert the edge. So the edge insertion itself will only take place in a fixed embedding, which is very simple. It's the shortest path in the dual graph. The question is, how do I find the best embedding? If we look at this graph, we may color it nicely to understand it a bit better. I want to connect the two red dots with each other, and you can see that the blue guys, I can kind of shuffle them around. I can change the order of the blue guys. And the green guys, they're also kind of three different pieces that I can reorder. And the orange thing, well, there's not much I can do about the orange thing. And when I now think about inserting the red edge, I may also see that these pieces here, they are kind of fixed, but as in the picture before, I'm able to flip this light reddish thing, and I'm able to flip this thing just on two different sides. So the question really is, when I want to insert an edge from one red point to the other, well, I'm going to leave out here, I'm crossing over the orange edge here, but what should I do now? Well, just when I look at it as a human, I will just see that there is this path of length 4 on the outside. I could just move that inward, away from where it's just in the way. And then I take this thick violet piece, and I may want to flip that around in order to get the red vertex on the outside. So I move this green thing in, and I flip the violet thing around, and then the red vertex will lie here on the outside, and then I will be able to connect it here with just a single crossing. How does the algorithm know that this is a good idea? Well, it computes something that's an SPQR tree. And this is just a shocking big tree. You're not supposed to understand it. If you know what SPQR trees are, be happy that it's drawn correctly, hopefully. Yeah, please.
Sorry, I got lost in the previous slide. What is the goal that we are after here? We want to add a new edge where the number of crossings in the total embedding is minimal?
Precisely that. We want to add this red edge, connecting the two red vertices, such that this red edge has as few crossings as possible, and the rest of the graph has no crossings.
And we already know to which edges in the current graph we want to connect that,
yes.
Yes,
so we do have these two vertices colored red, and we know that we want to connect these two vertices. Yes. So this SPQR tree is a decomposition of your graph into tri-connected components. If you don't know what it is, don't worry. It's just some kind of decomposition of the graph which describes parts of the graph in some reasonable way and just is of linear size. And the idea is that in this graph, when I'm looking for a path running through here, this actually is a path in your SPQR tree. There is the element of the graph which contains the one red dot, and there is the element in the graph that contains the other red dot. And this is a tree, so there is a unique path in this tree describing the different parts of the graph where you kind of run through when you insert the edge. And what happened here is, if we start from the blue guys down here, we were pretty happy with how it was embedded. We didn't want to change anything on this blue thing, and so we're happy down here. Then we cross over the orange thing with one crossing, and then when we get to the green parts, there is this reordering business that we want. That's something that will be encoded on one node of the SPQR tree, and there is the flipping, which just I can attribute to another node in the SPQR tree. Don't worry why this is the case. It's just what really is the interesting point that you should remember is I do have some magical decomposition where at the decomposition nodes I can attach a label that tells me what desire I have for a perfect embedding. Okay? And this is just along a path in this tree. For every point where I get past there, I can attribute how do I want the embedding to look. When does this fail? So when is the insertion problem really giving me a different solution than the crossing number problem? One of the simplest instances is here. What does this instance tell me? Well, my graph consists of kind of 3 large pieces, these gray things. Think about them as large grids. You're not supposed to draw them differently, because then if they would kind of intertwine, they would just have weird numbers of crossings. You draw them plainly as such. And you have additionally these 2 green edges. And this is essentially the unique planar embedding of this graph. And now you want to connect the 2 red dots. And for that, you need to cut from the inside to the outside. And the cheapest place where you could do that would be at one of these vertices and crossing half of its edges. So the red edge will collect delta half many crossings when delta is the maximum degree in your graph. That is the optimal insertion solution. You will require these many crossings. But the graph allows for a much smaller crossing number. If you just were to flip this component first, then you would just flip this component. So this dot would be on the inside and the red dot would be on the outside. Now you do have a crossing within the planar graph H. It's a stupid crossing. You don't need a crossing on H. But by the fact that you are now able to allow one crossing on the planar graph, you don't need any more crossings when you insert the red. So the optimal crossing number is 1. The insertion problem gives you a solution of delta half. And the interesting point is that this instance is essentially the worst case instance that there is. So Cabello and Mohar showed that the insertion problem will be an approximation of the crossing number with a ratio of delta half. But this is just for a graph which is essentially planar plus 1 additional edge. So it's not very interesting approximation algorithm because it's for such a restricted graph class. It would be much more interesting if we think about not inserting a single edge, but multiple edges. Well, if we insert multiple edges, then the problem directly becomes NP-hard again. So if I not add one edge, but an arbitrary number of edges to the graph, already solving the insertion problem is hard. There is a middle ground there. I can think about a special multi-edge insertion problem where all of the edges that I want to add are incident to one new common vertex. So I really want to insert a star into a planar graph. So you have a planar graph and you have a red star with a new center vertex and you draw that into the graph with the least number of crossings provided that the black graph still remains planar. That's the star insertion problem. And the star insertion problem with algorithms somewhat similar to the single edge insertion problem is able to solve the issue exactly again. It's not a linear time algorithm, and I won't tell you the exact polynomial because it's horrible. Again, the star insertion problem would be much easier to solve if I'm considering a fixed embedding for the graph in the beginning. So single stars is kind of the borderline that's still doable, although not very nicely, but arbitrary other edges, that's hard. And this insertion problem again fails to achieve the crossing number problem essentially with the same instances that you had before. You can just, instead of this one red edge, you just take a bunch of edges or have the star vertex somewhere in here. But you can again show that solving the insertion problem for multiple edges will be an approximation for the crossing number problem. It will not be too far away. It essentially, for every edge that you add, you have to add delta many crossings at most compared to the optimal solution, plus some additive term. If it's just the star insertion, then the ratio gets a bit better. So it would be interesting to solve multiple edge insertion, but the problem is hard, so what can we do? The original idea is the planarization heuristic. Very old algorithm from the mid-80s. You are given a graph, which is probably highly non-planar, and you just remove edges one after another until you end up with a planar graph. So you have some large, or perhaps maximal, or even maximum planar subgraph. With that you start, and then there are these edges that you remove from the original graph that you will now have to reinsert. And what you do in this reinsertion is you go through these edges to be inserted one by one, and let's say you start with the red edge connecting the two red dots. You add this edge in the cheapest way possible because you just resolve the single edge insertion problem. And when there is a crossing, you place a dummy vertex on it. Why do you do that? Because now after you have inserted the edge, you end up with a planar graph again, because you have this degree 4 vertex now in there. And it's again a planar graph, and in that planar graph, you can just iterate and add the next edge. So you add the next edge, you have two crossings, they are replaced by dummy vertices. You again end up having a planar graph, which is called the planarization, because it's a bit more than the original planar subgraph. And then you add the third edge, and you just iterate that, and hopefully you end up with a good solution. How far away can this solution be from the optimum? The same idea you can also do with just, instead of inserting edges, you can just insert stars, just to be quicker, and add more edges one after another. And this algorithm works unbelievably well in practice. This is essentially the strongest algorithm that we have to solve the crossing number in practice for really large graphs as well. When you do the star insertion, you don't bother with the SPQR tree implementation. It's too horrible. You just do it with a fixed embedding. And in either case, you do a lot of post-processing. So what you can do in this algorithm, once you're done, you have reinserted all the edges, you just pick one edge and remove it again and reinsert it again. And hopefully you end up with something better now. And you just do that with every edge, one after another, until at some point there is no improvement anymore. That's a very expensive post-processing, but it typically yields optimal or close to optimal solutions whenever we know the optimal. Therefore, it is surprising that this algorithm actually is bound to fail arbitrarily heavily. Think about this instance. What we see here is we have multiple gray structures connecting this top vertex to the lower vertex. And we can reorder all of these gray streams that are coming from top to bottom. And assume we are to insert the edge E1 and E2. If we think about it, we could just take this piece here, this gray piece, and move it to the left side, and then we wouldn't need any crossing for the turquoise edge. And we don't need any crossing for the blue edge either. So it's very simple to insert. But what if my graph did not have 3 edges too many, 2 edges too many, but 3? There is one other edge, which was also removed. And unfortunately, I'm going to insert this other edge first. And this is the red edge. And the red edge needs to go from the left-hand side to the right-hand side. It doesn't care about the order of these gray things in the middle, but it'll just run through them. But once it runs through them, it will place dummy vertices along its path. And therefore, it now fixes the order. Even though it wouldn't care about the order, it has to fix them because it adds these dummy vertices. And so it goes through here, and then there are probably 2 parts where it could cross over this gray piece, up here or down here. Perhaps it's just the same number of crossings, whether up here or down here I do the crossing. Just out of bad luck, I chose to cross over here. And now suddenly, adding the dark blue edge will have a crossing. If the red edge would have crossed down here, the blue edge would not have a crossing. But now it's unavoidable. And even worse, the turquoise edge didn't require any crossing actually, but now that the order is fixed, it collects an arbitrary high number of crossings. So that's why we know that in general, the heuristic cannot have any approximation guarantee whatsoever. What can we do to approximate the multiple edge insertion problem more effectively? Well, we can do it, and it's not a relative approximation, which is the typical approximation that you have. It is a relative approximation, like you need twice the number of crossings or 10 times the number of crossings. Here we have an absolute approximation. It's just an additive term of too many crossings that you add, and this additive term is only dependent on the number of edges that you insert and the maximum degree in the graph. So what is the idea? The key idea is to actually run the single edge insertion algorithm, but only parts of it. For every edge, you insert it individually without the other edges in this SPQR tree. This is the abstract way of our SPQR tree. And all we needed from the single edge insertion is that on every decomposition node in this SPQR tree, I have some desire for the red edge, for the blue edge, for whatever edge I add. It has a desire that is attached to these decomposition nodes. What do I want the embedding in this decomposition node to be like? So at every decomposition node, I collect the desires of the different insertion path, and then I go through these nodes and just take a majority vote. For every decomposition node, I pick one embedding, which is just the one that most of the inserted parts want. And that is the embedding that I then realize. And what the proof then does, it shows that if I have an edge that goes through some partial embedding, which is not just as I wanted it, but some other vote one, and I still have to traverse this decomposition node, I will need an additional number of crossings. But it will only require something like delta many additional crossings, or delta half, actually. And then I can show that, well, I am only not in the winning majority vote if I diverge from many other paths. So I go in a different way in the tree than most of the other paths do. Otherwise, I would have won in the voting. And you can show that these divergences are not too many, and there are only essentially k log k such diversion points. And every diversion point for an insertion edge needs delta crossings. And what the approximation completely ignores is the fact that these inserted edges cross each other. I don't care about that. Yes, they happen, but there are not many such crossings. It's at most f squared crossings, essentially. That's the idea of how to do the multiple edge insertion. And the powerful thing about it is that this algorithm is very easy to implement once you have the implementation for the single edge insertion, and it works very well in practice. Indeed, it works faster than doing the single edge insertion iteratively, because when you do that iteratively, after each insertion step, you have to rebuild your SPQR tree. And even though that's a linear time operation, it's an expensive linear time operation, and you don't need to do that. You only compute one SPQR tree for all of your insertions. Can we solve the multiple edge insertion problem exactly? Well, we know that the problem is NP-hard, but there is an FPT algorithm parameterized by the number of edges that I insert. And the idea of this algorithm is actually to just use this approximation algorithm. So we are again in this scenario. For every edge that I want to insert, I look in the path of the tree. What are the desired embeddings? And now I just don't pick any arbitrary vote, but I need to be more clever in order to really come down to the optimal solution. There are two issues that the approximation algorithm did not take care about. The one is, what if I have some bad luck with my voting? If you look in the world news, there is much bad luck in voting schemes nowadays. In our algorithmic scenario, we can fix that. We don't need to do a voting scheme, but we have a tree, and when I have a tree and I'm an algorithmicist, I, of course, do some dynamic programming on the tree bottom up. And that's something I can do. So I just run a dynamic program over the SPQR tree, which just fixes the best decision for every decomposition node. That's expensive, but it's parameterized in the number k of edges that I need to insert. And the interesting point is that typically with SPQR tree algorithms, the tough part is really in combining the different decomposition nodes. But that's a simple part here. Something that's typically easy in SPQR tree algorithms are this reconnected component case. But this is really the tough part. So whenever I just have a graph with a fixed embedding, adding multiple edges in a fixed embedding is already a hard problem. And that is because it's weird to estimate the influence of crossings of the newly added edges with each other. Like, do two edges that I insert, do they have to cross, or could they circumvent each other if they take different routes? And this problem is very much related to the famous disjoint path problem, which is NP-complete. So the problem in a given graph, find two paths which are disjoint from each other but shortest. It's a tough problem. This is very similar to that. But the difference is that in an insertion path, these paths may run in parallel to each other without touching each other. And this seemingly minor discrepancy makes it so that this problem becomes solvable, whereas the disjoint path problem remains hard. But this is kind of the simplest picture describing the algorithm who does that. And I'm not going to explain that picture to you. You need to think about homotopies in some auxiliary triangulation on top of a graph that already is kind of a triangulation. And it's a weird thing, and you have to check for all homotopies. And then it just boils down to the fact that because you only have few edges that you insert, and therefore few attachment points of these edges, it's kind of cheap enough if you just look at it from the theory side. But it's only on the theory side. In order to implement it, you're about to fail. I had a very talented PhD student once whom I asked to implement it, and after a couple of weeks, we quickly decided to give up on it. So what other approximations are there, apart from those that we have talked about based on insertions? Well, there is a very old approximation, also from the mid-80s, where actually they did not approximate the crossing number, but the term number of vertices plus number of crossings. And they argued that this would be a reasonable thing because application in VLSI design, full stop, believe it or take it. If you take this algorithm and turn it into an approximation guarantee, then this actually gives you an approximation guarantee for the crossing number where the ratio is, in O notation, something n to the log n squared. So the larger your graph is, the worse your approximation ratio gets. Can we do better than that? Well, in 15 years ago, Julia showed an algorithm that was the first sublinear approximation algorithm. It's n to the 0.9 times some polynomial in delta, and it's not the typical O notation, it's O tilde, which means we ignore all polylogarithmic functions in n. So this is just barely below linear, and what we see for all of these algorithms, even the one by Batt and Layton, is they have an inherent dependency on the maximum degree delta. So whenever delta is unbounded, and delta could be, the maximum degree could be in the order of n, then it always boils down to being at least an n approximation, or worse in that case even. So we're just thinking about this cozy feeling where we just have bounded degree graphs and think that these are interesting graphs already. and then you have a sublinear approximation guarantee. These were, so already this paper it appeared high class on Stock, I think, or Soda. Has a 12-page description. If you want to really understand the algorithm, there is no journal version of it. You need to read the archive version, which is a bit under 100 pages. Then there are several improvements, like essentially the square root of n, and the currently best is the first subpolynomial ratio, 2 to the log n to the power of 7/8 times some logarithms. It's a randomized algorithm. It also appeared at Stock, I think, so you can read it in 14 pages, or on archive. It's under 400 pages, but just barely. So there is no real peer review on the result. I hope it's right. I certainly didn't understand what's going on there. What I did understand for all of these algorithms, none of them can be implemented in practice. So that's quite unfortunate. What algorithms are there that can approximate the crossing number in practice? Well, there is one that is parameterized by a structural parameter, the skewness. The skewness is just a fancy word for the number of edges I have to remove from a graph in order to get it down to being planar. So that's just the multiple edge insertion problem, really. And there, that's what we just discussed before. We have an approximation ratio somewhere in the realm of k times delta. You see that you always have this dependency on delta. There is only one class of graphs where we have an approximation guarantee, which is independent of the maximum degree, but it's a very restricted graph class. If you think about graphs with path width 3, if you always thought all my interesting graphs have path width 3, then you're in luck, because then you can find a 2 approximation independent of the maximum degree in the graph. Unfortunately, most of you will think about other graphs as being interesting than bounded path width 3. Well, okay, you can do path width larger than 3. If the graphs are maximal within that path width, then you can approximate it independent of the maximum degree. Still nothing to be too happy about, really. And then there is another class of algorithms based on the genus of a graph. And that's the last algorithm class that I want to show you a glimpse of how they are working. Glynn and Salazar showed nearly 20 years ago that toroidal graphs can be approximated. And a toroidal graph is just a graph that can be drawn without any crossings on the torus, like on a donut shape. And they give an algorithm with a very simple running time of n log n. That sounds pretty pleasurable. And actually, it is a nice algorithm. There is nothing hidden in the big O notation. It seems like an algorithm you could implement if you were willing to. And it has an approximation ratio of essentially 6 times the square of the maximum degree. So if you think about cubic graphs being hard already, you do have a nice constant factor approximation. The whole truth is that this approximation guarantee only holds if something that's called the dual edge width of the graph is not too small, which intuitively means when you look at the graph embedded on the torus, it's kind of dense on the torus. It's not like there are very thin parts anywhere. And if it stands on the torus, then you get this approximation guarantee. It's not so essential. If you don't satisfy this property, then you still do get an approximation ratio. It's just a bit worse. A similar result holds for the projective plane. Like a projective graph is one that can be embedded in the projective plane without any crossings. And the projective plane is like if the simplest unorientable surface. It just has a single cross cap. But I really don't want to introduce unoriented geni in this talk because they just burn your head too quickly. So I'm not going to talk about that one. more interesting is that this toroidal case can be generalized to genus G graphs. So a genus G graph is a graph that can be drawn on some surface of genus G. So the torus is the genus 1 surface. The typical planar graph is the same as drawing something on the sphere. That's the genus 0 surface. And if you have any other genus G, then you can also find an approximation ratio, which has an algorithm in running time m log m. And the approximation ratio, well, it looks a bit more disgusting, but if the maximum degree is constant, as we assumed here, and the genus G is constant, up here we would have assumed genus to be 1 and only resolved that case. We can have any genus, and if the genus is constant, then this boils down to a constant factor approximation again. The ratio is horrible, of course. Again, there is a certain restriction that this bound only holds if the dual edge width is large enough. Otherwise, you get a somewhat weaker bound, but it's still applicable. The interesting thing probably is that the algorithm is not much different from the toroidal graph algorithm. The running time is even the same, really. It's just that on a toroidal graph, just like on a planar graph, you know, you only have 3 times the number of nodes is the maximum that you can have for your edges. And on the torus, yeah, well, you can have a couple of more edges, but it's still just a constant away from n. So whenever you're on the torus, you can just replace every m with an n in the big O notation. And you cannot do that on genus G graphs anymore, because for any fixed genus G, you also have a constant bound, but the bound just gets worse and worse. What is the key ingredient to resolve genus-based crossing numbers? The first starting point is to look at a very, very simple graph, or supposedly simple graph, the toroidal grid. The toroidal grid is the Cartesian product of 2 cycle graphs, Cn and Cm. So you can think about this being the graph. The vertices are always degree 4 vertices. And on the torus, you essentially have a cycle in this plane with a certain number of vertices, and you have cycles that are kind of curling around. These are 2 orthogonal cycles, one of length n and one of length m. And if you draw, why are you? Okay. Here I see a screen, so I can talk to myself. Let's hope it remains on now. So this construction is supposed to be optimal, but we're not sure about it. So the idea really is to just draw the long cycles concentrically, and then the short cycles in the toroidal grid you just draw here parallel next to each other, and then the number of crossings that you attain here is for, you have n times the small cycles, and every small cycle has its length minus 2 many crossings. That's just a natural drawing of a toroidal grid, and we assume that this is actually the correct crossing number for these graphs. We only know it when one of the cycles is really small, or when the longer cycle is much longer than the shortest cycle. Then we know that this construction is correct. Otherwise, we assume it to be correct, but we don't have a proof. The best bound that we have is close by. We know that a toroidal grid of size n times m cannot require less than half of that number of crossings. So the construction is optimal, at least within a factor of 2, which is good enough for our approximation, because that means drawing the toroidal grid in this way is a 2 approximation, and that's something that we know. But now we are starting with some toroidal graph, which is not a grid. So you have a torus, and you have a graph drawn on the torus. And let's start with seeing what the algorithm does. The algorithm is really a very simple algorithm. It looks for precisely the dual edge width, which visually means it looks for a non-separating cycle on that surface which cuts as few edges as possible. For example, it could be this red cycle here, and this only cuts a few edges. Like if I would go over here, I would cross over more edges, and I look for that cycle that crosses the least number of edges. And now when I have this cycle, I take my scissors and I cut along that cycle, and thereby I also cut the edges that are there. So these are the edges I cut, and my surface gets cut. So my surface now becomes simpler, because now this surface is essentially a sphere. It's just a weirdly stretched sphere, but topologically I don't have a handle anymore because I cut the handle. It's now a sphere. So I now have a planar drawing of the graph, except for the blue edges which I cut. So all I now do is, within that planar drawing of the graph, I look for a shortest path from this cut face through the rest of the graph to the opposing cut face. And now, for every blue edge that I cut, I can just route along this shortest path from the left side to the red side of the severed place. So how many crossings am I going to get? Well, if I cut k edges, and the length between this face and this face is L, then I'm now producing somewhat like k times L many crossings. Why is this a good algorithm? I mean, it's an algorithm that produces a drawing. We now need to prove that this is actually related to the lower bound that was attainable, so it's an approximation ratio. Well, the thing is that by the fact that this first red loop along which we cut was the shortest loop in the graph, and then we take the shortest path from one side to another, we can use that to understand that the original graph must have had a toroidal grid minor of length p times q, where p times q is not precisely k and L, but it's very related to it. It's a bit smaller than k and a bit smaller than L, but in the same realm. And I still see something. Okay.
He was getting tired.
So these p and q, the size of the toroidal grid minor, is still only dependent on k, L, and delta. And that's kind of the idea then, because we know that this toroidal grid minor, for that we have a lower bound, that p times q, half of that is the least number of crossings that I always require. And then there is another result that shows me that if I have a minor, which has a maximum degree of 4 in our case in the graph, and it requires a certain number of crossings, then the original graph requires a similar number of crossings. This is in general not the case. The minor could require many more crossings than the original graph, where vertices are contracted. But if the minor has a maximum degree 4, then this is the case. And, well, we are looking for a toroidal grid. Toroidal grid has precisely degree 4. So that's kind of the idea, that you know that there is a toroidal grid in that graph somehow, and that requires a number of crossings that is kind of the same as what our algorithm produces. And this then boils down to, well, it's just a factor of 6 times delta square off. Now, if you go to the genus G case, it seems like, okay, it's just the same thing again, because you just have a surface which doesn't have one handle, but multiple handles. G, many handles. This is the pretzel surface, and a graph embedded on it. And you now may think, well, in this graph, we only know about toroidal grids. We don't know anything about grids of higher genus. But if this graph requires a high genus, then there is a reason why it cannot be drawn with genus 0, and it cannot be drawn with genus 1. So there needs to be a toroidal grid in there somehow. So if I would just magically know what the largest toroidal grid in my graph is, I would have a lower bound on the number of crossings. And then the idea could be, well, I just cut through all the G handles, and so at the end, I just produce something like G times the number of crossings I assume for a toroidal grid, and the toroidal grid is in there. So this kind of relates the optimal solution to that the algorithm may do by cutting every handle to the lower bound. It's just off by a factor of G because I cut many more handles than just one. So there are multiple grids on there. That's the simple picture I might think about. And I cut all of these grids. And the largest grid is somewhere in there. And in the worst case, it's all large grids. The problem is that this is just wrong. You cannot prove it along these lines because this summary is just wrong. But it gives you the idea of what you try to do. The idea really is much simpler than the proof. The idea of the algorithm is you, again, start with the thinnest handle. You look for some non-separating loop on your surface, the red line along which you will cut. You cut up the surface becomes simpler. You got rid of one handle. You removed a couple of edges, and you just remember which edges you removed. And then you just iterate that. You again look for the shortest place where you can now cut it again, and remember which edges you cut, until you end up with a drawing on the sphere. And in that fixed embedding, you just insert all of the edges that you have removed in a trivial way in the fixed embedding. And that would be great if the last cut, like when you think about it, you always cut on the shortest distance. So the thickest handle, that will survive till the end, right? Because you always cut through the thinnest handle. You cut through a handle, through a handle, through a handle, and the last handle that you're about to cut will be the thickest one. And this should be the one which gives you a reason to believe that there is a toroidal grid of similar size in the graph. That's the idea of the proof. The thing is, that's not true. It could be that the second to last cut is much larger than the last cut, because while you are cutting, you're not cutting nice handles, you're cutting just anywhere on the surface where it's not too dense, which means you probably cut away parts of your large toroidal grid that is in the graph. Every time you cut away a bit of the largest grid in there, and in the end, the large grid is not there anymore, because you ate away from it piece by piece. But the nice thing is that you can show that after each cut, a reasonable fraction of the largest toroidal grid still remains in the graph. So yes, you are ruining the toroidal grid with every cut, but it remains in there, at least half of it, for every cut you take. So when you cut G many times, the toroidal grid is off by a factor of 2 to the G. That is kind of the idea why you get this approximation guarantee. Again, this is a simplification that's lying to you, because once you have a cut where you cut very few edges, you don't have, that's a proof that you don't have a high enough dual edge width. And all the proof logic in the Graph-Meyer theorems break down. But you don't need to care about that, because the funny thing is, if you cut along a curve where there are only few edges, then it's a constant number of few edges that you cut and that you need to reinsert. But that's just a multiple edge insertion problem again. So in that case, you can just go back to use the multiple edge insertion algorithm, because you know that this high genus graph has only few edges too much to be embeddable on a much smaller surface. And therefore, you get a similar approximation ratio even if you don't have the dual edge width that actually would contribute for the proof. So let me quickly summarize how all of these algorithms behave in practice. We already said that the planarization heuristic, which just remove the edges that ruin the planarity for you and then just reinsert them one after another, that's just a very, very good heuristic in practice. And it's actually the only heuristic in practice that we have available. And it works very well. It typically finds optimal solutions, or at least close to optimal solutions, and you can rerun it a couple of times with heavy post-processing, and you'll mostly end up with optimal solutions for those graphs where we know the optimal solutions. Of course, we cannot talk about the others, but it seems reasonable that it should be close there as well. And there are certain things that you need to do to make them very practical in purpose. In practice, one thing is you need to do some pre-processing. The other thing is you need to do some post-processing. So the machinery of the insertion should only be applied on a graph that was shrunken before, so that all the simple parts are already out of the way. That's what the non-planar chord construction does, also SPQR-based. And then you have this post-processing, which means that, as I said before, once you're done with your solution, you just, again, remove stuff from this planarization and reinsert it. And you just do that a couple of times until there's no further improvement. And that then is, of course, a question of how much time do you want to spend on the algorithm and how good do you want the solution to become. The best algorithms in practice are either you do the single edge insertion iteratively, with very heavy post-processing. That is kind of the slowest algorithm, but it gives you very, very good solutions. The multiple edge insertion approximation that we discussed is much faster and gives you essentially the same quality as the single edge insertion, but much faster because it doesn't need that high number of post-processing steps. And then there is a surprising third contender, which is much simpler to implement. You don't do anything of this SPQR tree stuff, which we don't understand anyhow, right? We just insert stars into a fixed embedding. But just by the fact that you're not inserting one edge after another, but always a whole star, and you do this with post-processing, you end up with very, very good solutions in practice and very fast algorithms. If you are looking at graphs really with thousands of edges, then building and rebuilding the SPQR tree becomes a bottleneck in your algorithms. And then there are multiple things that you can do. There is dynamic SPQR trees, so you can not recompute the SPQR tree, but just update it after the insertion of an edge. And this works. It shifts the applicability of the approaches a bit, but not by a huge amount. Or you just drop the idea of doing single edge insertion and you use the multiple edge insertion, because there you only need to build the SPQR tree once and not for every edge that you insert. And if even that becomes too expensive at some point, you just do insertion on a fixed embedding and you won't get the optimal numbers, but you will still be quick to get good solutions. For the genus-based algorithms, the picture is a bit weird because the actual approximation algorithms, they are rather simple. So looking for this loop along which we want to cut is actually a well-understood problem, and it's not hard to implement once you have the embedding of the graph on the surface. So once you would have the embedding of a graph on the surface, you could implement these algorithms. The problem is generating an embedding of a graph on a higher surface. Well, in theory, linear time algorithms. Age-old linear time algorithm, very beautiful for the toroidal case. No one has ever managed to implement it. And I know 2 or 3 research groups who have tried. It's just tough to implement that algorithm reasonably. And there is no implementation as of yet, so therefore the genus-based approximations, we don't know how well they would perform in practice because we can not generate good embeddings for them. And then, yeah, I already discussed, there are exact approaches that are feasible if the graphs are small and simple enough. There are many, many open problems in graph crossing number. In particular, in graph theory side of things, but I only focused on the algorithmic part in this talk, so therefore I only want to talk about open problems in the algorithmic world. There is a huge discrepancy when I think about approximation algorithms, both in terms of what are practically applicable and what are not, but also what is in theory attainable and what is not. We do know that there is no p-TAS, so we cannot approximate the problem arbitrarily close. And the best approximation for general graphs we have is, well, it's only for maximum degree graphs. For general maximum degree that's not bounded, we don't know anything. If I have bounded maximum degree, then there is something that's just slightly subpolynomial. We don't know whether there is a constant factor approximation for crossing number or not. We neither have a lower nor an upper bound. That's one of the largest questions in the algorithmic realm in terms of crossing number, already for the bounded maximum degree case. Is there any approximation that can be done in practice apart from the insertion algorithms? We don't know of any. And even if I look in the heuristic space, I don't care about guarantees. I just want an algorithm that works well in practice. Just any idea. Despite the fact that the planarization heuristic has been around since the mid-80s, so that's like 40 years ago, it is still the only algorithmic idea to figure out good crossing numbers of graphs. There is no other algorithmic idea that produces reasonable results. None. Come up with any idea, and everyone will be happy. Are there any parameterizations beyond the crossing number and the weird vertex cover number of a graph, both of which do not turn out to be helpful? Are there any parameterizations that are practically relevant and not enormously super exponential in the parameter? We don't know of any. And for the exact models, we only have these two ideas. We either make the graph very large or have these linear ordering polytopes on every edge in order to resolve their realizability problem. We don't have any other idea to formulate the crossing number problem in the mathematical programming world. Any other idea would be very welcome, but there is none as of now. Perhaps you're going to change that. And of course, if you're not into algorithmics, crossing number is a rich field of other questions as well in graph theory, or just go the route of doing variants of the crossing number, like one planar crossing number and stuff like that. And with that, I want to thank you for the attention. And if you are keen on this kind of research, we do have an annual workshop on crossing numbers where we meet every year as a group of people who are interested in this stuff somewhere in the world. And if you're interested in that, you can talk to me later about it. Thank you for your attention very much, and have a pleasure. Great.